Hello. Okay, so we are actually going through the 2024 paper today. So we do as a do with me. I'll be going paper one and paper two together. So for those of you who are stuck, please go and watch this video. Watch and we do together. You take this as a revision. For those who are available, who are strong enough, I suggest you go ahead yourself. Okay, you don't watch this video. You try to go ahead. But you use this video as a means as you are marking and for you to go through your corrections to understand why you do wrong, you get things wrong. You can just toggle here and there. But for those of you who have nothing, you really cannot start. At least the very least, let's start watching this video, go through this together with me. Then after that, let's go through the thinking processes, right? What are the important things that um what are the important concepts or the important things and what actually the question is actually asking for, right? And then especially for paper two or especially for the MCQ section, right? With your MCQ section B and section C, especially for section B and section C, right? When we do section B and section C, at least you know what are the important things that you need to say to in order for you to hit the right points, right? And get the marks. Okay, so without further ado, let's begin. Question one, the student investigate how the temperature of a beaker of water changes with time as it is heated, and then shows the readings on the stopwatch as he reached different temperatures. Okay, so these are the stopwatch, right? This time at 70 degrees, time at 100 degrees, time at 30 degrees. What's the time taken? So we know that it is almost 2 minutes, not exactly 2 minutes, right? But you must remember that seconds, there are 60 seconds, all right? So it is 1 minute 54 seconds. Okay, don't make the mistake of taking 540 minus 346, right? And then you get some different answers. Yeah. Okay. Question two shows a distance line graph. Shows the distance line graph below shows the distance traveled by a moving car. What is the average speed of the car from 0 to 5 seconds? Now, every time we see distance time graph, okay, always remember, every time we see velocity graphs, right, we see speed time graph, kinematics graphs, right, first thing we do is write D, S, A, distance, speed, acceleration. Okay, if it is a, then after that we know that it's a distance time graph, right? So if it's a distance time graph, you go and circle D because it is a distance time graph. So we know that for information that we can get the distance information, we can also get the information about speed. But how do we get it? So please remember, if it goes to the right, it is gradient. Okay, we take the gradient. Most of the time we take the gradient. Or we can take the gradient. Okay, it is a speed time graph. Then we go and circle speed. Right? After you circle speed, then you know that to the right is gradient and to the left is distance. We take the area. So you want to find distance, I take the area. If I want to find acceleration, I take the gradient. But it's a distance line graph, so you want to find speed, we take the speed. Okay? Now, then they say, what is the average speed of the graph? Average speed. Every time you see average speed, go and write down the formula. You know the average speed equals to total distance divided by total time. I need distance, I need time. Do I do I need speed here? No. Right? I don't need speed. So average speed, always remember, we don't go and find the speed here and then find speed here and then you take half of it, or you divide by 2. No, that's not how you find average speed. Average speed is always total distance divided by total time. So what is the total distance here? Total distance here is 40. Total time is 5. So you get your answer. Okay. Let's move on. Question 3, again, it is a kinematics graph, right? So if I have kinematics graph, Always begin with a D, S, A. Now we are looking at speed time graph. And they want acceleration, so we're going rightwards, so we want gradient. Okay, we want gradient. So if you want to get gradient, yes, speed, yeah. And then you want if you're so we need to look at the gradient to see increasing acceleration. So increasing acceleration means we must see an increasing gradient. Okay, so we want to see an increasing gradient. So which one gives me an increasing gradient? Does this give me an increasing gradient? No, this one we know that it's traveling at constant speed, right? Because no increase, so no acceleration. This one gives me a constant gradient, so it's constant acceleration, right? Constant acceleration. For C, how does the gradient move? Is initially it's like this, and then it's like that, and then it's like that. It's getting gentler and gentler, so the gradient is decreasing, right? So it is D whereby we see that, sorry, it is D whereby we see that it's going upwards, right? So this is our answer. Yeah, because it's increasing acceleration. Important for us to understand, yeah, whatever that is going. So as you watch this video, please, if you need to, go and repeat. That's the reason. The good thing about having this on video is you can actually watch again. Try to think through the thinking processes. Okay, so question 4. Pumped out until it's vacuum and then released as it drops, right? What quantity remains constant? This one, always remember that acceleration when there is no air resistance, or negligible air resistance on Earth. When there's no air resistance, or when there's negligible air resistance, right? Air resistance, right? On Earth, the acceleration on Earth will always be 10 meter per second squared. Constant. It will always be constant. Okay, so we know that it's acceleration. Let's go through the different acceleration. No, it's not acceleration. Displacement is going further and further away. Displacement is higher. Speed is getting faster, right? Velocity is also getting faster. So that's why the answer is acceleration. Okay. Question 5. Object moves to the right with acceleration. You see there are different forces here. It's accelerating to the right, right? Object has no weight. It's not true. Resultant force is 0. Cannot, because there is acceleration, right? There's acceleration, so we know that F equals to ma. There is an acceleration. If the acceleration is to the right, force must also be to the right. Resultant force, sorry, F net. Yeah, F net must also be to the right. So it cannot be there's no F net, but yes, resultant force is to the right. This is the right answer. All forces have the same magnitude, not necessarily. Okay? Not necessarily. You see all this going to the right, so somehow it's pulling to the right. How can this force be equal to the different forces here? Because this force needs to give a bit of the leftward force, right? Okay. Question 6. Two identical bars are dropped separately into two identical containers containing two liquids X and Y. After some time, the content in the container settled like that. Okay. So we know that what we say this is, you see that is in like floating, sinking. We know that the topic is, which topic? Has to be density, right? So we look at density, we know that the bar is less dense than X because it floats on X. But the bar is more dense than Y. So you will look at that. Y, then bar, then X. X being the most dense. So which one follows this? Bar is less dense than liquid X. Oh, this is correct. Just check the rest. Liquid X is less dense. Liquid Y, no. Liquid Y is more dense than the bar, no. Liquid X and Y have the same density. That's not true. Okay. Question 7. 4 objects are put in a tank of water which has a density of 1 gram per cm cube. Which object will sink? Okay, so we can go and find mass and volume. So they give you these two quantities. Maybe we need to go and find the density using the formula rho equals to mass divided by volume. So go and find out, calculate, and if this is sinks means which object is more dense, right? So go and find, do the calculations and go and find out yourself. Okay. Question 8. Silver has a density of 10 gram per cm cube. A cube of pure silver is cut into 8 identical pieces, right? Which statement is true? Always remember, material the same, density will always be the same. Because it's the same material. No matter how big, how small, density will always be the same. This is a very important principle. If it's the same material, density will always be the same. The mass may be different. Volume may be different. But the density will always be the same. Okay, so the answer is C. Okay, let's move on. Question 9. A child sits on a 50 Newton box to rest. Base of the box, total area of 2 meters squared. Okay, remember this is, we are talking about area. This is area, so we know area A is equals to 4.0 meters squared. Child weighs, this one is 450 newtons. Then the box is 50 newtons. Okay, weight of the child is 450, weight of the box is 50 newtons. What is the pressure exerted by the child on box on the floor? So pressure, you know, is P equals to F over A. Formula that we have to memorize. Okay, so P equals to F over A. Force, we know there's a 450 newtons, 50 newtons. So we know that the combined force by the due to the two weights is 500 newtons. Then you divide it by the area, which is 2. Okay, so always have the habit when you see the different values and they tell you values, write down what this value means. Right, so you know that the weight of the box, either you indicate in the diagram or go and write it down, 450 newtons. This is weight of the box. This weight of the child, right, is 50 newtons. Okay, so go and indicate this so that when you come and put in the formula P equals to FA, oh, I know immediately what are the different values I have already. I know which one I can substitute. Okay, that's question 9. Let's move on to question 10. Right, nail hammered into a piece of wood. Which statement best explains how sharp tip helps the nail get hammered into the wood more easily? Why? So every time you think sharp tip, hello, sharp tip, blunt, they use the word sharp, they use blunt, they are probably gonna test me on pressure. It's probably on pressure already. Sharp, tip, blunt, small area, big area, right? More or less is going to be talking about pressure, right? So we know that smaller pressure, a smaller area means bigger pressure, right? So higher pressure, immediately we know that is higher pressure. It's not on the greater force. It is not on the about friction. It is not about the, we are going to talk about pressure. Okay. Question 11. Boy swinging on a rope tied to a branch tree from A to B. What is the boy's energy in the kinetic store given that his mass is E is 50? So M equals to 50 kg and his speed at B is 5. So V equals to 5.0 meter per second. So they ask you for energy in kinetic store. Energy in kinetic store, what's the formula? EK equals to half mE squared. The formulas, I really need you to go and memorize. Memorize the formulas, practice doing them on the papers, right? Even if you are done with the paper, go and try again. If you have been referring, try again without referring. Reinforce your memory. Having the formulas is going to give you a good chance of you to pass or do well. If you don't know the formulas, you're not even going to answer the question. Memory, it starts from there. Go and memorize the formulas first. Okay, so energy in the kinetic store equals to half mv squared. You have M, you have V. It's just simple application of the formulas. Question 11 done. Question 12. What are the changes to the energy in the gravitational potential stored in the kinetic when it accelerates up a hill? Okay, accelerates tells me that V is increasing. If the speed is increasing, we know that, what do we know about the kinetic energy? The speed increases, the kinetic energy will also increase. And they use up a hill. Now it's also going up the hill. So if it's going up the hill, height is increasing, right? It's moving up, 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 up. That means the gravitational potential energy also, this one will also increase. Okay? So the answer is increase and increase. The answer is yes. Question 13. Equal boxes of equal weight onto a platform. Girl lifts boxes of weight. Which one will not affect the work done by the girl? Okay, so there's boxes, they has the weight going down, right? Work done, we know, is force times distance. Okay, so height of the platform, yes, it makes sense because this distance must be at the, something special about this distance is that they must be at the same direction of force. Okay, yes. Number of box lifted, yes, because affects the number of box, yes, because no matter how many number of box, the more the number of box, the more she actually do work, right? Because there are more boxes, more weight that she carried. Okay, the weight of the box, yes, but the time, there's no indication of time. Okay, so we don't care about the time here. Okay, so the time, the answer is C for this one. Right, because the sign for, because time, don't confuse work done with power. Okay, so power, yes, you'll be using more power if she takes lesser time. Question 14. Air is contained in a metal cylinder which is free to move. When it is heated, piston moves to the right. What happens to the air molecules when the metal cylinder is heated? Okay, air, when metal cylinder is heated, piston moves to the right. Okay, first thing first, metal cylinder is piston, we know that the temperature is increasing. Okay, so every time you think about, they talk about heat, and then you see molecules or particles, we have to think about the internal store. And when we talk about internal store, we think about two things, right? Because it's your thermal store, right? Internal store, there are two things. It's the EK, the kinetic energy of particles, and the potential energy of particles. Every time they talk about change in temperature, we talk about the kinetic energy of particles. Every time they have talking about the state, either it's solid, liquid, gas, is changing state, we talk about the potential energy of the particles. Okay, so in this case, they are talking about it being heated. So if it is being heated, we know that temperature is increasing. So when there's temperature increase, we go back to the kinetic store. So we know that kinetic store means particles are, there's increase in the kinetic store. Immediately we know that they are moving faster, right? Kinetic energy, right? So it's moving faster. Okay. Question 15. Which rule gives the most appropriate distribution for the forces of attraction between solid, liquid, gas? So we know that solid is the very strong, liquid, it will always be this way. It increases this way. Forces of attraction, right? Solid has the strongest, right? Increasing this way. So it's P. Question 16. Ice is heated. Again, ice is heated. Immediately I know temperature increase. Can immediately write there EK increase. Just quick jot down already. Okay, I know that temperature is increasing, kinetic store is increasing, and its temperature is measured. A graph is plotted to show how the temperature of ice change with time. So over here we know that, oh, this one EK increase. Here temperature remains the same. But it's being heated. So why it remains the same? So every time you see a temperature time graph, you see that there is constant temperature. Two things can happen. Number one, if there is constant temperature, that means temperature don't change. There are two possible scenarios. Number one, it is at room temperature. That means it has reached thermal equilibrium. This one, it will not change anymore. No more changing. Once it reaches thermal equilibrium, it will stay in that room temperature unless you continue to heat it or you continue to cool it. So in this case, is it room temperature? No, because after that it increase and you are constantly heating the thing. So it is not room temperature. Number two, it can also be a change of state. Okay, so now just now you see that this is ice, right? So this is solid, this is liquid. So this is when it turns from solid to liquid. Again, so remember whenever we talk about internal energy, there are two types of internal store. Energy internal store, we have two, which is the kinetic energy of particles and the potential energy of particles. EK talks about temperature. EP talks about state. So is there a change in state? There is a change in state. And it's being heated up. That means energy is being transferred into the internal store. So if the energy is transferred into the internal store, we know that the potential energy is actually increasing. Internal store actually increases during this time of X. But you can see that the temperature remains constant. So because it stays the same, we know that the EK also stays the same. So I know I'm going through a lot here. The answer very simple. Internal store increase, temperature increase. Why am I going, Starkman, why are you going through the whole thing over and over again? The reason why is get used to this. Get used to this kind of thinking so that if you encounter tougher questions, you encounter this in section B, right? A common question they like to ask you is, why does the temperature not change? Explain using energy the changes in the temperature during period X, for example. Why does the temperature of X does not change? Right? So these are important things that we need to know. So go back to this. Help this thinking frame. I see temperature time graph, or whenever they talk about these heating questions, cooling questions, questions involving temperature, thermal physics questions, right? Think about your internal energy. Know that it can be, we see it in two different times, or there are two types of internal energy, or it's made of two components, the kinetic store of particles and the potential store of particles. Link the kinetic store of particles to the temperature. Obviously, it is the relationship of the kinetic store of particles is with the average speed, how fast the particles are moving. And the potential store is the separation, how far they are apart. But translation, it means when talk about average speed, I'm talking about temperature. When talking about how far apart, we are talking about state. Okay? So this is the link that I need you to start to have in your head and practice having this in your head, because this will help you as you attempt your thermal physics questions. And once you are able to grasp this, right, grasp these thinking frames, you will see that thermal physics questions are not difficult. You don't need to do many algebraic gymnastics. Don't have to interpret so much on the questions. Sometimes the Newtonian physics, you tend to all the calculation. You have to, sometimes they give you and then you have to reinterpret what it means. Wave, sometimes you have to interpret, right? But when it comes to thermal physics, it actually is quite straightforward. Okay. Question 17. Which statement best explains the term internal energy store? Okay. All right, we talk about internal energy store. See just now. So internal energy store again split into two things, EK and EP of particles. Okay, so the sum of the kinetic energy of the particles and the potential energy between particles is the sum. Question 18. Double glazed window is shown in the diagram. Okay. Now, every time you think about, you see airspace, right? It's a big given to you. Every time I see the word airspace, it's a very big given to you. I see air, I know like wear fur, everything they think they trap heat, right? Why wear blanket? Because they traps air. Why is this a big given? Because every time you think of airspace, think about it being a poor thermal conductor. So we know that it goes into conduction. Okay, so probably we're gonna have to talk about conduction somewhere here. Okay, so let's see which statement explains why the double glazed window can help to keep an air-conditioned room cool in Singapore's weather. Glass allows infrared to pass through very well. Why do we need to talk about the infrared, right? Then it becomes hotter, right? Glass absorbs energy from the sun slowly because poor thermal conductor. Yeah, but glass not really. Glass is a solid, so it's, do you know that this is not the case? Air trap between the inner and outer glass reduces the amount of energy by conduction, right? The air trap between the inner and outer glass prevents hot air from flowing in, or the inner and outer glass. So we know that it is T, more of T, not preventing the. Why do you need to talk about the flow of hot air going in? Okay, you don't have a window, or you have a window, so the air not gonna come in, right? It's just putting one lid there, like prevent the air from coming in. Okay. Question 19. Paper clip X put in the same position. Spoon X, spoon Y. Observe that the wax on spoon X melts faster than spoon Y. So this one melts first. So immediately, what can we say? This one has to be conduction. Right? It cannot be radiation. Why? Because radiation, this is solid. We don't really, yes, this part is radiation from the flame to the spoon. Yes, it's radiation. But how about it travels all the way to the wax? That one needs conduction. Okay, it cannot be convection. Definitely not convection. Right? So the answer is D. Last question. Heating element is to be positioned. Okay, heating element which was to heat a sealed tube of liquid. We know this one, we are going to look at convection. So heating element, always remember. In order best circulation, okay, so the answer is D. Heating is to heating element, we put it below. Cooling element, we put it on top. Right? In this case, heating element, so we want it to be at the bottom. Right? Okay, and if you need to draw the convection current, it will look like that. It needs to be a loop. Okay, C will only be one small loop here. Okay, it's not as effective. Okay, we are done with the MCQ. So 20 marks done. Yeah, another 30 marks to go. You want to take a break here, but let's continue. I'll just continue. If you want to take a break, pause the video. Okay, question 1. Details give some units of energy. Complete the table by filling the blank space. Joules, kila, giga. Okay, we must remember this one. The girl make kids delicious cookies, making me healthy. Right? So this is your Tera. Okay, this is Tera, giga, mega, kilo, deci, centi, milli, micro, nano. 3, 6, 9, 12. 1, 2, 3, 6, 9. Okay. So this one will have, this is the small m. So this one is your millijoule. Gigajoule, we know is a GJ. Right? And then kilojoule, we know is times 10 power 6. So it's times 10 power 3. So it's 3 zeros. Okay. Question 2. Say and explain the temperature of energy between Okay, diagram shows a pendulum swimming freely between positions 1 and 3. Say an example of the transfer of energy between the energy stores as it moves from position 1 to position 3. Okay, so in this question, right, we know that as it goes here, EP is going down, EK is going up, and it's go here, EK will go down, EP will go up. So you can break it down from 1 to 2. You can talk about these two, that the energy from the potential store is transferred to the energy of to is from the potential energy is transferred from the potential store to the kinetic store, right? Mechanically due to work done by gravity, and then and from 2 to 3, energy is transferred from the kinetic store to the potential store, right? Mechanically due to work done by gravity. Okay, so this is, make sure you have that. So as long as you break these two down, talk about these two things, you'll get your full marks. Okay, your full 2 marks here. Question 3, 2B, right? Carries out an experiment, 10 swings on a pendulum, repeated or pendulum length, and then he put the time for the swings, right? Show the mark the plots. Okay, one good habit first is to know what these plots actually indicate. Okay, so we know that. Okay, one good habit is what each interval indicates. So let's say this is 0 to 10. Can I try 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, just nice. So I know every small line is 1, right? How about this? Every small interval, is it 0 0.1, 0 0.2, 0 0.3, 0 0.4? But it's not 0 0.5, it's 1. Okay, so I need to change. It's not 0. It's not 0 0.1. Let's try 0 0.2, 0 0.4, 0 0.6, 0.8. Nice, just nice one. So I know every small interval is 0 0.2. Okay, so when you plot, make sure you plot it properly. For example, 0, 0, make sure you plot this inside. Okay, then after that, 10, 6.2. So 10 is here, 10 is here, 6.2. So 6.2 is, so it's 0 0.2, right? So 10, 6.2. Okay, and then you do the rest. Okay, so they tell you, they already hint to you that it's a curved line, so you just go and draw a curve. That's it. You can do a bit freehand, but it should be relatively, it should be smooth. Okay, go and make sure that you can do the plotting, yeah. Suggest what Aiden can do to improve the accuracy. Standard, if every time you want to take measurements, right, to do it, take multiple readings and then take the average. A crane has a mass of 9,000 kilo. Write this down first. M equals to 9,000 kg. Diagram shows a crane and a worker in the construction site. Okay, the crane rests on 2 caterpillar tracks. Okay, these are the caterpillar tracks. Both caterpillar tracks have a total area of 8.8 meters squared. So 8.8 area, immediately go and write this down. Area is 8.8 meters squared. Difficulty, the worker has difficulty walking on the muddy ground because his feet sinks, or his feet sinks into the mud deeper than the tracks of the crane. See why the crane does not sink into the mud even though it is much heavier than the worker. Right, so we already probably guessed that it has to do with about the area. So we talk about in these kind of questions, right? Sinking, floating, either density, but in this case, we are not talking about density. It doesn't make sense for us to talk about density. We talk about pressure instead. So pressure equals to force over area, right? So we talk about how we need to say that why the crane does not sink. So the crane has a much larger area, means than the worker, larger contact area than the worker, therefore exerts lesser pressure. Okay, so you talk about the contact area is 1 mark, you talk about exerting lesser pressure is the other mark. Okay, given that G is 10 newtons per kg, calculate the weight of the crane. This one, again, you need to go and be familiar with your formulas. W equals to mg. Substitute in. They give you G. They give you M. We know the M just now. We have the M on top. Right? So we go and substitute them. And calculate the pressure exerted by crane. So it's P equals to F per A. Next question. Question 4. Diagram shows part of a roller coaster track. The mass of the roller coaster is 2500 kg. Mass indicated already. Okay, mass of the roller coaster is 2500 kg. Okay, so they say calculate as the decrease in the gravitational potential store is moved from X to Y. Okay, so we know that the decrease in the gravitational potential store, we know that this one we use the formula EV equals to mgh. As it moves from X to Y. So from h equals to 25 to h equals to 5. Right? So we use the formula EP equals to mgh. EP is equals to mgh. Mass, we know what's the mass. Just now we have the mass. 2500 times A times 10. G on Earth, you already take it as 10. And the height is this difference. Right? And you will get your answer. Okay? Now the next one, they ask you to, due to friction, 1000 joules is transferred from the kinetic store to internal store. Calculate the increase in the kinetic store as it moves from X to Y. Okay, so we know that it's moving. Whatever, okay, this is a very important thing, is that the energy, the decrease in the gravitational potential store goes into the kinetic store. So energy is transferred from the, as it goes down, right? Energy is comes, okay, maybe we write down here. So from X to Y, we know that EP is decreasing, EK increase. Ideally, all that's in EP goes into EK. But in this case, it is not ideal. Why? Because they say 100,000 joules transferred from the kinetic store to the internal store of the surroundings. So we know that what is the value here. Okay, so this one actually your answer should be 4,000 joules, right? Sorry, 500,000 joules. Oh no. This is 500,000 joules, huh? Your answer here is 500,000 joules. So we know that it is just ideally it's 500,000, right? But 100,000 is being transferred, so you only get 400,000 joules. Okay. At a particular instant, the speed is 12 meter per second. So we know V is equals to 12 meter per second. Calculate the kinetic store. This one is very simple. EK equals to half mv squared. You know the m, half, definitely you know half. So, and now they give you V, it's just a simple substitution of values. Okay. Okay, let's go to question 5. Cooling curve. Cooling curve now. So immediately I can, if you want to immediately write this down, internal store is made up of your kinetic and the potential store of particles. Okay, so this is related to temperature. This is related to the state. Okay, from substance Y cooling down from 70 degrees to a room temperature of 30 degrees. Okay, you know that there is a change of state here. Constant temperature, right? We know there is a change of state. You know what state? I don't know, right? But there is a change of state here. Okay, so let's look at the rest of it. At 70 degrees, substance Y has a molecular arrangement that looks like this. What does this look like? Okay, this looks like this is a liquid. Describe the molecular arrangement of substance Y at 70 degrees. Okay, so guys, it's important for you to know your F, FAM of your solid, liquid, and gas. Okay, go and be sure of your FAM. Force is the force of traction, A is your arrangement, and M is the movement. So it is closely packed in an irregular arrangement or disorderly arrangement. Okay, you can see less closely packed or closely packed in an irregular, or you can see disorderly manner. Okay, name the process. So if this is at 70 degrees is liquid, if this is liquid, this is gas. So liquid to gas is known as, this is liquid. This cannot be gas. This has to be solid. So this is liquid to solid. The process is called solidification. Describe the change, if any, to the internal potential store of substance Y at 45 degrees. So at 45 degrees, there's a change of state, right? It is going down. It is a cooling curve. So internal store is decreasing. So because internal store is decreasing, we know that the decrease in energy in potential store. Can? Question 6. Okay. Did I skip? 2, 3, 4, 5, 16, 70. Okay. Question 6. Explain how energy from the heating element is transferred throughout the water. It is to the water. So every time you see it transferred throughout the water, it's transferring around the water. You know, this has to be on this talk about convection. Transferring throughout liquid. Every time you say transfer throughout liquid or throughout a fluid, right? We know that we're going to talk about convection. This says passes through or transfers throughout the solid, then we talk about conduction. So we have to explain how convection works. We need to talk about your density. Okay, so every time you have convection, a few things we need to explain. First, you must explain either number one, we talk about the energy. Is the energy increasing or decreasing? In this case, energy is increasing. After we say that it is gaining energy gain, right? Then remember we talk about VD, volume density, the change in volume, the change in density, rising or VDR, the VDM or VDM, right? We talk about VDM. What does VDM means? There's a change in volume. So how does the volume change? It is increasing in energy. So the water, not water particles don't expand, but rather the water near the heating element, they increase in volume. So we say volume increases. What about the density now? VDM. Density decrease. Movement is it rises. Then the next one, what happens to the denser particles on top? So talk about the denser particles, or not denser particles, sorry. What happened to the denser water? The cooler, denser water will movement is it sinks. So your energy, first talk about energy and then VDM. These 6 points will give you your 3 marks. Okay, your 6 points, or in this case, it will be 2 marks. Okay, so you must say that the water near the heating element increases in temperature. Okay, gains, sorry, gains energy, E done, and expands, done, causing its density to decrease, done, and rise, done. Right? Then you say the denser, cooler, denser, water sinks, done, setting up a convection current. Okay, the last one you need to talk about convection current. They might want you to mention the word convection current. Convection current. Okay, either 2 or 3 marks, you have it now. Okay, can? So it's really not difficult. So it's a bit more tedious, I understand. But whenever you describe convection, remember it is this part. EV, they will have talk about energy first, and then VDM, DM. Okay, volume, density, movement. Density, movement. And you wrap the whole thing up by saying that this sets up a convection current. So if it is an ice instead, they put ice, for example, on top. How does how does it cool the whole liquid down, right? So having the ice, right? The water near the ice, right? Water near the ice cools down. So water near the ice loses energy, or loses energy. You can see loses energy, and therefore it contracts, causing its density to increase and sink. Okay, can? Okay, state one reason for using metal casing of a kettle. Why do we want to use a metal casing for a kettle? Right? This one doesn't make sense now if you want to say that it is it is a good conductor, good thermal conductor. Because if you're going to touch, what happens if you touch? Right? In this case, it is more because the benefit of a metal being of a high melting point. Okay, but shiny smooth texture. I see shiny smooth. I thought see the word texture. Right? You remember this, right? You remember TACT? Either they talk about temperature, they put surface area, or they talk about color and they talk about texture. We are going to talk about radiation. Right? So why the need for a shiny smooth texture for the outer casing? Number one, when you talk about radiation, who is hotter? Surroundings hotter, or the kettle is hotter? Kettle is hotter. So if the kettle is hotter, is it emitting or absorbing? Right? So if it's hotter, remember, if the object is hotter, it emits. If the object is cooler, it absorbs. Right? So we know that it's hotter. So we know that it is emit. So it is a poor emitter of thermal radiation. Okay, guys, section C. It's the last 2 questions. Just hang in there. Okay, let's just hang in there. Okay. Box was pushed along a rough surface by a force. The motion of the box was recorded in a speed time graph. So they give you a speed time graph. I see this, I'm going to write DSA. So I'm going to write this first. I know this is my gradient if I want my acceleration. This D is if I want my area. Just have this habit. Just write down first. Okay, and you may need it, may not need it. It's okay. Just write it down first. Okay, so state the principle of conservation of energy. 3 things. Conservation of energy. You must tell me that cannot be created nor destroyed. Okay. Right. Only transferred from one store to another. And that total energy of an isolated system is constant or remains the same. Okay, hitting these 3 points gives you your 2 marks. Describe the energy transfer between from 2 to 3, 2 seconds to 3 seconds. So it's somewhere here. 2 seconds, 3 seconds. Energy, you can see that speed is going up, right? Okay. So we can say that here, energy is transferred into the kinetic store. But by whom? By how? From where? Maybe a chemical potential, like the person pushing, right? So we know that the EK increase, but we must always account from EK to increase. Something there must be something to account for it. Okay, so maybe there is the chemical potential energy somewhere will decrease. Okay, mechanically due to work done. P part 1. Calculate the acceleration of the box between T22 to T23. Okay, remember it's here. It's the same. It's constant acceleration from 0 to 5, so it's the same. So we can just take A equals to, take the gradient, rise over run. So it rises up by 8 and it runs by 5. Okay, so you will get 1.6 meter per second square. Describe the acceleration of the box at t equals to 6. So let's look at t equals to 6. T equals to 6 here. Acceleration, I need to look at the gradient. Let's look at the gradient. Is there any gradient? No, it's a flat line, so it's constant. So if we just say that, so it's not even, it's 0. So it's 0 acceleration. Calculate the distance traveled by the box when it is moving at constant speed. So we are looking at here. Oh no. Constant speed is this one, right? So if this is constant speed and then I want distance, so I take the area. So it's just 8 times 12 minus 5. So distance is 8 times 12 minus 5. Okay. And you will get the value. Can? Last question, question 8. The diagram shows a toy rocket with a mass of 0.2 kg. Gravitational, so mass equals to 0.2 kg. Gravitational field strength is 10, so G equals to 10. Moves vertically upwards when the motor in the toy rocket provides an upward force called upthrust. State 2 differences between mass and weight. This one need to go back. Many different differences. We talk about mass, we talk about weight. We can have difference by definition. We have the differences by the SI unit. We have a difference by scalar vector. Like mass is a scalar, weight is a vector. We have difference by the dependent on location or on G, gravitational field strength. And also we have differences in terms of the measuring instrument. This one, go back to our notes. Okay. Question 2, assume air resistance, draw free body diagram. So no air resistance means there's nothing that is opposing it. So we have an upthrust that's pushing it forward, upthrust. And you must also include weight. Okay, don't forget there's always the weight of the rocket. From the rocket takes off from rest. So you can, initial speed is 0 meter per second, U equals to 0 per second. and reaches a speed of 5 meter per second. So this V final speed 5 meter per second in 2 seconds. T equals to 2.0 seconds. So calculate the acceleration. Just nice. E equals to V minus U over T. Okay. Calculate the resultant force of on acting on the toy rocket during the first 2 seconds and assume the mass of the toy rocket remains constant. Resultant force. So you have F net is equals to MA. Do I know the mass of the toy rocket? Did they give me the mass? Oh yes, I did give me the mass. See? So this is important information that you need to go and write first. So that when it comes, I just need to look for A. Do I have M or not? Do I have M? Then say immediately I see M equals to 0.2. Okay, so I know that this is 0.20. And the A, where do I get A? A is I get from here. Okay. And that's it. That's all I have. And this is the 2024 paper. Continue to bring your compilation book, please. So from next lessons, right, I may not be around, but you need to bring your compilation book, right, and you can do your 2023 and 2022 paper. Okay. All right, that's all. I wish you the very best, and good luck and continue to revise. Okay, start doing thematic revisions, right, and I suggest for you to once in a while to go and try questions. Okay, if you are done with the paper, there's no harm repeating the question again, right? Maybe if you first need a video, try without the video. If you are good without the video, then keep trying try yourself. Okay, so that's all I have today. You can go and redo all the other questions, all the previous J1, J2, J3, or redo the J1, J2, J3 in the compilation book. Okay, that's all I have for you. Thank you very much. I will see you midweek 3.